Okay, so let me show you variation of mega parameters. Yeah, so this is actually just variation of parameters, but in 2 dimensions instead of 1. Okay, so the kick with variation of parameters for second degree equations is that you get a little extra tool, and you just have to know that it's there. Okay? So the idea of this, right, is I have some equation like y double prime plus p1 of x y prime plus p0 of x y equals some f of x, right?
Sure.
Yeah? Okay.
Yeah.
So if I knew one of the solutions, right, I could use reduction of order to find the general. Right? If I knew 2 of the solutions, which seems like the case that I'm more likely to be in, because like if I can hunt down one solution, I probably can find the other one basically the same way. You guys with me on that? So this works in cases where you have this guy, and you know y1 and y2 solve how? y1 and y2 solving the homogeneous version. Right? You guys good with this? Okay. So, what would variation of parameters done in one-dimensional style be? We just did 2 of these, come on. What's variation of parameters usually? Like, how do you do that? Yeah, you guess some function you don't know times the homogeneous solution, right? Okay. Alternatively, you could think about that as replacing the constant in the homogeneous solution with a function, right? Like that would be another way to think. So in this case, I might look at this and be like, okay, so the general homogeneous solution is like C1y1 plus C2y2, right? Let's pull that.
Yeah.
Right, so this is just me thinking, okay, I have y1 and y2 that are a fundamental solution set for this thing, at least for the homogeneous version.
So I just want to make sure, like, when we're doing variation of parameters, we have to have 2 solutions to the homogeneous.
Yeah.
Okay.
Yeah, if you don't have a fundamental solution set, like if you don't have 2 solutions to the homogeneous equation, do reduction of order instead.
Okay.
Right? That's if you have 1.
That's the difference.
If you don't have any, then you gotta sort out that first, right?
Figure out
And
what it is.
yeah, so once you sort that out, you'll get either 1 or 2 solutions depending on how you get it. If you get 1, reduction of order is the jam. If you got 2, then variation of parameters is a good idea.
And if we still haven't been given a way to solve
Yeah, you have it.
non-constant coefficient homogeneous ones.
Yep, don't worry about it. Nothing to see here. That's not the problem you're looking for. This is the problem you're looking for, because this is easier. So, instead of guessing this, right, for variation of parameters, I'm going to guess y is mu1 y1 plus mu2 y2. Does that seem like a natural guess? Like, given that you know how to do variation.
Though, right?
What's that?
Like mu of x.
Yeah, so these are mu of x's, right? So basically, I just looked at this thing and thought, what if the constants varied?
That's a good idea.
No, it's actually a terrible idea, but it turns out that it works. So the kick of this is, what do I do from here? Like, once I've made this guess.
Differentiate y twice.
That would be
Yeah.
my guess.
Okay. So it seems like you should differentiate y. Oh, but this is gonna You guys see
Can we
that?
do two separate
So,
and add them?
yeah, so we need two separate product rules and then to add them. So we're going to get mu1 prime y1 plus y1 prime mu1 plus mu2 prime y2 plus y2 prime mu2. Right? Okay, and this is the thing. It seems like I now have a lot of stuff to play with, right? So the good news is that there's a trick you can use for variation of parameters, which is you can look at this whole thing and be like, dude, I really don't feel like playing with mu1 primes and mu2 primes. So what I'm going to do is I'm going to take those and I'm going to assume this thing. I'm going to assume that mu1 prime y1 plus mu2 prime y2 is 0.
See, that's like, why?
Why?
Why? Good. Basically,
Oh, because we
There's-
y1 and y2 solve.
there's a lot of possibilities in terms of functions, right? Like, I replaced two constants with two functions. You guys see that? That was like too big a jump in degrees of freedom. You could have tried. What if instead I replaced YH? Like, what if my guess was just mu times YH, right? It would turn out that's not enough. So there's kind of a Goldilocks problem here, right? One good guess might be this one. Another good guess would be y is mu times c1 y1 plus c2 y2, right? And you don't really even need both constants. You could get away with one of them because you'd absorb one into mu. You guys see this? It turns out this is like too small. Like this is the little chair in the front room for Baby Bear. And this one's too big.
Is it too big in that like it's insolvable or just that?
It's too big in that when you do all this stuff, right? If we made this, we kept continuing in this fashion and made this substitution. In the end, we'd get a pair of second order differential equations that I'd have to solve, right? And I'd come up with two different versions of the first problem I started with, and I still wouldn't be able to go anywhere. Cool? So there's a too small option, Baby Bear option. There's a too big option, the Papa Bear option. And so it turns out that if you start with the Papa Bear option, and then never mind, this analogy got away from me. I don't know how to make Papa Bear smaller. And I don't want to imply that doing this would make it, yeah, whatever. Started with an overture that was too big, right? So you got some pillows for it, basically, to make it medium sized.
It looks like, I mean, that right there makes it, I know it's not true, but it makes it look like mu1 and mu2 are constants.
Yeah, it kind of does. So this is basically me saying, all right, I'm going to assume some stuff about mu1 and mu2 to make it so that this doesn't give me second order stuff. It's possible that this technique wouldn't work, right? Because I made this assumption. Like, it's entirely possible that this assumption's too much. It turns out that's not the case, but it could be. It could be that if you make this assumption, you just can't solve the differential equations you get at the end. They just don't make sense. Which is what would have happened if we had done this one. If we had done this one, we would have gotten unsolvable differential equations. Which wouldn't work.
And so what was like the methodology or justification for picking that assumption in this case?
In this case, if I assume this, or my motivation at least,
Okay.
is that mu1 prime is gone now, right, from this guy. So when I differentiate again, I'll at worst end up with mu1 primes. And then I'll be looking at a first order equation that I can have more hope of solving.
So rather than assuming, is it more like hoping?
Kind of.
Like,
Yeah, so my hope is that by assuming this, I'll still end up with something I can solve. it turns out that's going to be true, and you just need to remember that this assumption is the right one.
Like, this seems like something that some mathematician, like, just, like, tried and it worked.
Yeah, but remember, variation in parameters was that thing too, right? Variation in parameters is like, well, what if it wasn't a constant? What if it was a function? Would that work? And it turns out that it did.
But you didn't put a restriction on it like you're doing here. It seems like you're forcing this, and it seems like you would eliminate a lot of possible functions, right? In doing it.
Yeah.
Are there other solutions besides this constraint?
No, it turns out that this will be enough.
And so you're getting a unique solution?
Mm-hmm. But the only reason I know that is because there's an existence and uniqueness theorem for this, not because this was the only possible way to do this.
It's so weird to see what it works.
Yeah, it's super weird that this works.
So did they do like the too big one a bunch of times and then just realize that those canceled, or is we just?
No, because if you do the too big one, these don't cancel.
Okay.
There's no reason that they should cancel.
Okay, that's what I was wondering. Just the justification is confusing for me because there's no reason they should cancel, but we're just saying they do.
Yeah, the justification is not. This is a little bit like partial fraction decomposition. There's not a justification for why that method works. You just check it every single time and it works.
This seems like something where you would.
This is the same thing.
Okay.
There's not a good justification for why this is going to work, but it is going to work. Does that make sense? Like partial fraction decomposition is weird too. Okay? Okay. So if you assume those are 0, then your y prime is just y1 prime mu1 plus y2 prime mu2. Right? Okay. So then I need y double prime, right? And my y double prime is going to be O, and now this time I'm going to have to do a product rule, and I'm not going to get to make an assumption. So on this one I'm going to get y1 double prime mu1 plus y1 prime mu1 prime plus y2 double prime mu2 plus y2 prime mu2 prime. You guys good with this? And then I need to shove all of that stuff into star, right? Okay. So I'm going to write that a little bit.
Excuse me.
Yeah.
Just for notation, I don't know if it's going to make a difference, but they started off with y double prime times p sub naught x. Then they went p1, p2 because they end up with a formula at the end that it equals your second equation equals f of x over p naught. And you get your p.
Oh, and so my equation is going to be different than the one in the book?
Yeah,
okay, so let me adjust my equation to match the one in the book so I don't screw it up.
There you go.
So P1 and P2.
Because those will cancel out.
Sorry, that's a good point. I should at least match the book. So if I match the book's notation for my equation, I could, of course, get to the form I was in, right, by dividing through by P naught, right, and then relabeling some things, but I should end up with the formula in the book. So I got my y double prime, which needs a P naught on it, right? So I have P naught times all of this stuff. And then I have plus P1 times the y prime stuff without this thing I assumed is 0. And so I got y1 prime mu1 plus y2 prime mu2. And then I have plus P2 times mu1 y1 plus P2 times mu1 2 y2. And the whole thing's supposed to be f. Oops, and I guess I dropped the of x's on everything else, so I'll drop it over there too. Okay, now, the cool thing is, you might notice that it certainly seems like there's a whole bunch of P zeros, ones, and twos kicking around in there.
If you distribute it, there
Or if I distribute it, there would be. Okay, fine, I'll distribute. Gross. I'm gonna screw this up, and it's your fault, Alex.
I didn't
Want
tell
to
you
know
to.
that.
Why are you distributing?
Yeah.
I don't know, because Alex said I had to distribute.
I didn't. I said no such thing.
It sounded like you did, so now I am, and I'm blaming you. Okay, so distributing all of this jazz together, and then what am I going to observe?
A lot of cancellation, hopefully.
Yeah, hopefully a whole bunch of this stuff goes away, I hope. So if you go through and you look for, what am I looking for?
Your equal zeros thing?
Homogeneous thing.
Yeah, go look for the homogeneous equation of star, right? So like, okay, so the homogeneous version of star should look like P naught y double prime. Okay, there's a P naught y1 double prime. Is there a P1 y1 prime somewhere?
Yeah.
So P1 y, yes, P1 y1 prime. And then is there a P2 with a y1 in it? That one.
Oh, everything with the
Oh, and all of those are multiplied by mu, thank God, right? So that whole thing is the homogeneous version. So all three of those terms are not themselves zero, but together they're zero, right?
Cool.
And then, okay, if I play that same game with y2s, right? I want a P2, P0 y2 double prime. That one.
Yeah.
Then I want a P1 y2 prime. Got one of those.
Yeah.
You're right.
Okay. And I want a P2 y2. You got one of those. And again, all of those have the same mu2 coefficient on them, so those all zero out. And again, it's not that they're each themselves zero. Oops. Dang it. Not that one. It's not that they're each zero, right? It's that they add to zero. Why do they add to zero?
Because we said so.
Because they're homogeneous.
Because they solve the because they are the homogeneous version of that, at least times a function, maybe. Okay, so all told, in the end here, you end up with this equation. P0 y1 prime mu1 prime plus P0 y2 prime mu2 prime equals F. Right?
How come your zeros are different colors again? Was that was a two different homogeneous equations?
Yeah. So
Yeah,
the blue,
ones and the mu2s.
if I can find my blue mark, it's in one of my pockets, I swear. The blue is because y1 solves star homogeneous. Right? And then the pink is because y2 solves star homogeneous.
And we just know that because it said you have a y1 and a y2 that solve.
The homogeneous version of star.
Will that normally be given to us, or do we have to go solve for a y1 and a y2?
So for now, those will be given to you.
Okay.
You might be able to find a way to get those on your own. One of the things we're
Oh,
gonna
that sounds
like
so awful.
the next thing we're gonna learn. The next thing we're gonna learn is how to Laplace transform, which will give you some tools to go fetch these.
So once we fetch those, then we decide if it's variation or reduction of order, then
Yep.
we do all that other stuff?
Yep. Yep.
Sick.
This is why engineers work in groups, right? You do not want to be the poor guy that is like left at the office when your boss barges in and goes, I need you to solve this differential equation quick. Right? You want to be the team that shows up in the morning with coffee. Right? And goes, wow, Jim, you solved that by yourself last night? Dude, good work. You forgot a plus C.
In
Right?
the third step.
Third step. Yeah, we'll see you tomorrow.
You gotta see when you're finding the y1, sorry.
Okay, so right here, you end up with this other thing, okay? Which bears some superficial resemblance to the thing we started with assuming, right? You guys see that? Okay, so divide this thing through by p0. So you get y1 prime mu1 prime plus y2 prime mu2 prime is f divided by p0. You guys cool with this? So my claim for variation of parameters is that three things should go on your notepad. Or notepad. This one, and this one. So the short version of variation of parameters is those are the ones you want. Oh, what else? This.
Yeah.
Right? Because you're going to want to remember what your form of your guess was. Cool.